Hello and welcome to this next lecture on machine learning. In today's lecture, we will introduce you to unsupervised learning with the specific example of dimensionality reduction. We have already discussed supervised approaches to dimensionality reduction. We will see what it means to do dimensionality reduction in an unsupervised manner. So recap supervised feature selection. We discussed greedy feature selection based on criteria such as gain, information gain. We had talked of information gain with respect to criteria such as entropy, Gini index and the classification error. We have also discussed optimally selecting a subset of features using iterative hard thresholding for classification, lasso for regression and so on. Question is, can we avoid depending on the class label for dimensionality reduction? So what if one wants to do dimensionality reduction independent of any class based supervision? For example, I might have a text document. The text document could be review on drama, and the review says, I loved the second scene. It was mind-boggling. Now what you find here is that an adjective such as loved, and what you find is that keywords such as loved and mind-boggling are highly correlated. Could we discover their association based on their co-occurrence? So could we discover associations between features based on their co-occurrence? It is very much possible that this particular text snippet was a positive review on some drama. However, I would like to keep this class label called positive review hidden from my algorithm. So let us see how this could be done. We will try and build upon one hot encoding for characters that we had discussed in the context of recurrent neural networks and LSTMs. With 3 characters in the vocabulary, we had discussed the best encoding to inform each character occurrence to the network, or one possible encoding, the one hot encoding, where we give a unique key k to each character in alphanumeric order and encode each character with a vector of vocabulary size. So there was just one for the element that was actually present. With 3 characters, this is how you would have one hot encoding. Now what happens if you have words instead of characters? So A could be loved, B could be mind-boggling, C could just be seen. Now seen could be equally correlated with keywords such as loved and hated, whereas mind-boggling and loved are very strongly positively correlated. Can we discover this in the encodings? Could we learn a representation for loved and a representation for mind-boggling such that in the space of this representation loved and mind-boggling are very close together? So how to encode the words for a task of labeling drama reviews as liked or not liked, where we are going to treat these reviews as hidden. So for example, review 1 could be: the drama was interesting, loved the way each scene was directed, I simply loved everything in the drama. It's very positive. There's a second review: 3 boring hours, very boring to watch. In fact, it's possible that a keyword like 3 indicating the length of the drama could also be negatively correlated. It's also possible that a keyword such as 3 indicating the length of the drama could be strongly correlated with the sentiment such as not liked. And going back to the third, we have all positive keywords, especially loved the performance of actor. Now the fourth one is interesting, where the person says that I hate all dramas by that director, but does talk about an exception here, which was this particular drama that he watched. There was a lot of entertainment. How do we capture the correlations between the words in the reviews independent of the class label? Through word embeddings. So how to encode the words for a task? Through one hot encoding. Well, first of all, we will move slightly away from a one hot encoding to also factor in the count of a word. So we will use the word frequency instead of just a 1. So loved, boring, liked, hate, entertainment and so on are counted along with their frequencies, and this is a bag of words representation where the order does not really matter. So there are of course limitations to the bag of words, because first of all it is possible that each word occurs a few times and overall there are lots of words that occur, and as a result the vocabulary size is very large. So with this kind of representation, your encoding for every single word would be as long as the size of the vocabulary. The second problem is that we are unnecessarily ignoring contextual similarity. Liked and loved are contextually similar words, but somehow that is ignored in the bag of words model. So we are posing the following question: how do we learn a model of interplay between the word representations given the context even while ignoring the class label? So let us start with a simple possibility. Let us say we pass a one hot encoding of the word as the input to a neural network and design the output layer of the neural network. So what happens? We will start with a very simple model. Let us say the input and the output of a neural network are basically copies of each other, in the sense that the input has the same structure as the output. For example, the input could be all the words that occur in a particular context in their one hot encoded form, and we are trying to basically predict the words effectively in the output structure. We are going to do that through some hidden layer or sets of layers. Now, what is the effect of copying the input patterns also as training data on the output side? This basically is the idea behind an autoencoder. What's happening in the process of encoding the input into the hidden layers is the process of encoding. Encoding generates an abstract representation for the concrete input. Decoding, on the other hand, goes from this abstract representation to the concrete output which you want to be decoded. What we discover in the hidden layer as a result of this encoding and decoding is correlations or associations between the different attributes. So this is the architecture of a simple neural network autoencoder. The input layer and the output layer have a similar structure, and the hidden layer encodes associations between the signals in the input layer to help you recover the output. In fact, it not only helps you recover the output, but it also helps you generalize the recovery process. So here are some desirables. Let's say we perform some unsupervised training with some online data. Can we discover that a king minus man plus a woman is actually a queen? Or that if Paris is a capital of France, then Tokyo should be the capital of Japan? In fact, the capital relation was implicit, and so was the head of the state relation in the first case. So here is a hypothetical word vector representation that could help us achieve the desirable. We would expect that the encoding of king in terms of the hidden layer gives you different measures along different dimensions. So the first dimension is a measure of royalty, the second is a measure of masculinity, then of femininity and age. The king certainly scores well on the first, second and the fourth dimension. The third dimension is negligible. We would actually like this to be 0. On the other hand, queen scores very high on the first, third and the fourth dimension. Princess, on the other hand, scores well on the first and third dimension, but poorly even on the fourth dimension. A woman, on the other hand, is just scoring well on the third dimension and nothing significant on the first and second. Woman could be ambiguous, could be grown up, or could be young. In the case of one hot encoding, the size of the representation, the dimensions, would be as many as the number of words. But it's possible that just 4 or something of that order suffices for purposes such as identifying the gender and the position of a person in society. So what could be the vector for man? Well, as far as man is concerned, we would like the masculinity to be high, age to be around 0.5, score low on femininity and on royalty. Now are we able to recover that by the simple algebraic operation? Now is it possible that we can recover the representation for a queen based on this simple arithmetic operation, king minus man plus woman? Or if king is to man, then queen is to woman? Try these out. So the first case, what you are interested in is vector subtraction and addition, and the second case, again we are interested in matching the vector differences of both pairs. The following vector representation for man seems to be sufficient for these equalities to approximately hold. So the basic idea of embeddings, or more specifically word embeddings, is to build a low dimensional vector representation from the corpus of text which preserves the contextual similarity. We want to be able to play with words as numbers, because numbers is what deep neural networks can understand. So what will the training comprise of? We will continue sticking to the continuous bag of word models, which means that we are not overly concerned about the order of the words. So what you do is take words in one hot encoded form. For example, the top V frequent words are used to represent each word, and then you take a word window around each word to train the neural network with context words C set as input and the central word W as output. So for example, your C could be I really the drama, and the output that is desired is liked. And you want to be able to discover is a hidden representation for the context such that you are able to reliably predict the desirable output. This is the general architecture for training the embedding model. You are training it, but it is still unsupervised because you have not really associated any human supervision in this process. So the training consists of continuous bags of words. You are associating context with every word. So C1, C minus 1, C2, C minus 2 are respectively contexts with shifted windows, and what you want to do is be able to predict the word in its one hot encoded form, and in the process you basically train the hidden layer with different correlations amongst these words and their representations. One question is, what if we wanted the hidden layer to obey some structure? So let us say the hidden layers corresponded to masculinity and femininity respectively. This certainly is a case of nearly orthogonal embedding. On the other hand, if your embedding was, say, masculinity and age, they are highly correlated, and therefore this would not qualify as an example of orthogonal embedding. So how do you make sure that you discover orthogonal embeddings and discard non-orthogonal embeddings? One possibility is principal component analysis. So if X is a random vector and gamma its covariance matrix, principal component analysis is based on finding a rotation of the original coordinate system and expressing X in terms of that system, so that each new coordinate expresses as much variability in X as can be expressed by a linear combination of the n entries of X. So one solution to this problem is principal component analysis. So let X be a random vector and gamma its covariance matrix. Idea of PCA, principal component analysis, is to find a rotation of the original coordinate system and express X in that system so that each new coordinate expresses as much as possible of the variability in X. Now how can this variability be expressed? Well, here is an assumption: it as can be expressed by a linear combination of the n entries of X. Now the coordinates by intuition should be such that they are orthogonal. So the orthogonality comes somewhat here, but we are also interested in prioritizing the coordinates, which means we want the first coordinate to capture the direction of maximum variability, the second to capture the next maximum direction of variability of X, and so on. That means you are trying to come up with a data driven transformation. This can be used for feature discovery, feature selection, and so on. So embeddings can be seen as a generalization of PCA. The solution to PCA, of course, cannot be obtained through simple backpropagation. In fact, the solution to PCA can be described in terms of the normalized eigenvectors E1 to En of the covariance matrix gamma. The n principal components are basically E1 transpose X, E2 transpose X, and so on. If you are only interested in capturing the k components of maximum variability, you would restrict your attention to E1 to Ek. Here are some homework problems for you. So let X, the random vector, be generated using a vector of Gaussians. So Px1 is Gaussian centered around mean 0 with standard deviation 1, ditto. Similarly, x2 is also Gaussian centered around 0 with standard deviation 1, and let us say the covariance between the two random variables x1 and x2 is theta. You should find all the principal components of the random vector x, the two dimensional random vector x. Now let us say you have another random vector y, a multivariate Gaussian. This multivariate Gaussian is centered around the 0 mean vector with a covariance matrix which is the identity matrix plus a small shift. Try and find at least one principal component of y. I again add this disclaimer that PCA cannot be recovered through simple backpropagation on embeddings. However, you could think of PCA as a specific example of the embedding model. Thank you.